Thank you. So this is great. I get to talk rubbish for 20 minutes to a captive audience. My dream come true. It's probably why I wanted to become a lecturer, I guess. Anyway, so it's true, I do apply mathematics. What can I say? Could have been worse. I could have been French, something like that. It's great to be doing the interlude now because I can finally do Famelab with slides. I know you envy me, yeah? So I'll be talking about my research. We're going to do some citizen science, and then there'll be an interlude within the interlude, and then we'll wrap it up. How about that? Yes, how did I get there? Sometimes I'm asked, why did you do this, Michel? Why are you doing maths, applied maths, physics, chemistry, all of this? Is it because, you want to understand the world around you, the universe, the planets, all of this? No, it wasn't. It all came because one day, I was just 14, I was in secondary school, and I was a bit of a loner, but this beautiful girl, I remember her name, Sandrine. Hope she's not seeing this video now, but she came at the end of the maths class and she said, listen, Michel, I didn't get that thing about quadratics. Can you explain it to me? So I said, yeah, sure, let's sit down. I did it. And she said, oh my God, this is so simple. You make it so simple. You should be a maths teacher. And I thought, maybe if I do maths more and I become a teacher, maybe girls would be interested in me. Well, it doesn't work that way. So let me show you my trajectory. Yeah, sometimes I present this to secondary school students. And so, well, by the time I finished my baccalaureate, as it was called, I was more into physics. So I went on to do a primary degree in physics. So all of these years, then I became a qualified teacher. That took another year. Then I took a break. And I actually went to Dublin to work in Edinburgh. Why Dublin? Why Ireland? Any guess? Because of a woman. Yes. Did that for 1 year. By then, I was just sick of studying. I said, that's it. I want to do something useful. I just want to wash dishes. And I did that. And it was great. I loved it. After that, my country called. At the time, there was still the national service, so I was sent overseas for 2 years. I did what I had to do. And then I came back to Ireland. You know why now? And I say, you know what, before I teach, I'm just going to wrap it up with a master's. And that was great, actually, going back to studying after a long break. For the first time, really, I really enjoyed studying. I really loved it. It was the best studying year in my life. So I did that for 1 year. And then finally, I became a physics teacher. I taught in a secondary school for 1 year in France. But I missed the excitement of research. And so I decided, got married in France, and then I decided to go back, to Dublin for the same reason again. And I did my PhD in applied maths. At the time, it was called mathematical physics. It's disappeared now, so I'm going back to maths now. That was great. And then, look at what happened. Positions all over the world to finally become a permanent researcher here at NUI Galway. So this was 20 years ago I started. It took me 10 years to get there. It was hard. I suffered a lot. I can tell you it's much harder now. So think hard before you want to go into academia. Anyway, did you notice anything special on this slide? Yes, right? What happened there? Yeah, once I showed that to primary school teachers, students, and they said, oh, you made a typo, you copied and pasted twice the same line. No, I didn't. I repeated, yes, because of another girl. That's, she was really, really good looking. Another thing you might have noticed is that I broke up my study and I took breaks, and for 3 years first, and then for 1 year, and yet I managed to do a career. So that's the message I want to tell you. You can have accidents, and you can still bounce and finish your studies. You can take breaks and still build up a career overall. Message of optimism. Okay, enough about me. I'm going to tell you now about the work I do, and it's mostly about the mechanics of soft tissues. So typically the brain, the cardiovascular system, the skin, all these things, I like to treat them as if they were just, engineering material that you test in the lab. And then the idea, so I'm pretending to click here, but there's no connection, it's just too far. So Andrew is guessing, every time I go like this, oh. So the idea is that you test the material in the lab, you get the properties, and you feed them into what's called a finite element simulation. It's just a computer simulation that's just going to help you predict what happens, for instance, inside the brain when you have an impact. Yeah? Very interesting from the point of view of medicine, because they can just run trials for free, basically for free, and they can imagine all sorts of scenarios, all sorts of impacts, all sorts of, I don't know, procedure or treatment, and see what happens in the simulation. But of course, the simulation is only as good as the material parameters that you feed in, right? So you need to do good experiment, good robust experiment, basically physics experiments, good standards to get those qualities. Okay, so I'm going to show you 2 ways of testing the brain. The first part is called destructive testing. You will see why. And I call this part the mechanics of a twisted brain. And it's literally the mechanics of a twisted brain. I like the word literally. My daughters always use the word literally. Oh, Dad, I'm dying. I'm literally dying. No, you're not. Anyway. So, sorry, I should have warned you. There's going to be gruesome images of pieces of brain. These are not pieces of brain from humans, from PhD students or whatever. They're just from slaughtered animals. Basically, I got them from the slaughterhouse. I didn't harm the pig myself. It was already done, yeah, after the fact. In fact, brain is not in the food chain in Ireland. Did you know that? Is nowhere to be found, not even in animal food. It's been completely removed. And so if you go to a slaughterhouse, they will just give you brain for free if you want, I don't know, to play with that. Yeah. I brought one with me. I like standing like this one day. Angus took a, fantastic, thank you, oh, he's doing it. Fantastic picture of me going like this. And, I feel like I'm a cross between Hamlet and Hannibal. Standing like this. Yeah. Anyway, so brain is pretty soft, it's pretty hard to test, but there's one test that works well, it's called the simple shear. It's like a classic protocol in material testing. What you do is you just shear the brain, you measure how much force it takes. Anyway, I won't go into the details. Let's go to the next. Yes, you get that type of graph, and then you measure the slope, and the slope tells you the stiffness of the material. That's the type of parameters I need to feed into my computer. So we did for the brain, at the bottom there, very low slope, right? You remember how to compute the slope? y1 minus y2, x1, etc. We did it for gel, and we found that the slope of this curve here was 20 times the slope of the brain. And so we were able to conclude that brain is very, very soft, right? So when people tell you, are you a bit soft in the head? You could just say, matter of fact, I am. Right? And then I got so excited about it that actually I wrote a paper here. You can see my name in the Irish Times. Yes, they said it. Up to 20 times softer than gel. I thought I'd made it in Irish society when I managed to write an article. Look at this. Ta-da! Yes. That's what I thought. But it didn't stop there. This article was then taken as a subject of study in this book. Anybody going to secondary school? A cousin or a young brother or sister? If anybody has the C.J. Fallon book, you look up on page 103. I made it in our society. Come on. Yes. I thought the loop was closed now. I always wanted to be a teacher, and now I'm in the textbooks. It doesn't get any better than that. Okay. Now, remember I was telling you about twisting. So there's simple shear, that's an easy one. And then twisting is much more delicate to realize, but we managed to do it for brain as well. And the idea is not that you cut out a cylinder, you glue it top and bottom, and then you twist one plate with respect to the other, and you measure how much torque it takes to twist it that much amount. Basically same idea. So I'm going to ask you a question now. I'm going to do citizen science. Just tell me what your intuition is using the same app. So if Andrew could show you now. What about this question? So let's say I have a cylinder, a full cylinder made of something soft, like, I don't know, say rubber, for instance. And I'm twisting it. Yeah? What do you think will happen to that length L? If I twist it, will the length increase, the length decrease, the length stay the same, or I just don't know, I just don't care anyway. Think of that question. So, hopefully, this coming up now. Is it coming up? Yeah, okay. So let's enter the results. I need this for my grant proposal, guys. Help me out. And then I'm going to show you the actual answer. Personally, when I was thinking about that question, I didn't have any gut feeling for it. Maybe I thought of twisting those cans of beer. You know, they always seem to crush a bit. So maybe I would say shorten. Yeah. I don't know what you guys say. What we did is this experiment here. That's in my office. Nice view on the quadrangle there. So here we have a 1 meter long rubber rod. At the bottom here, this is just a weight. It's made of lead. And there is the pointer. You can see here, yes, did you see that the bar was at that red mark, right? And I'm just twisting to, let's do it again. It's at the red bar. And I'm just twisting, yes. So if it's going to lengthen, it's going to go down. It's going to shorten, it's going to go up, yeah? Makes sense. I'm twisting. The things we do for science. Look at this. Yeah? It's short, it's lengthened, sorry, right? It's higher up. So if you twist, it lengthens. In my opinion, it's counterintuitive. I look forward to seeing the results of the poll, see what you meant, what you found. So we did that. I know you're like, where is this going? We did it for the brain. We twisted it, but the plates, they don't go up or down. So if it's going to expand, and the count is going to push up on the plate, right? And we actually measured that. That's the so-called pointing effect. Here it is. We actually found out that if you twist the brain, it's going to create forces vertically like this. And then, on the next slide, you can see that we fed that into computer simulations, a bit like I was showing you earlier, and we imagine a scenario where the head is twisted violently like this. 2,000 radians per second minus. That's the kind of rotational acceleration you experience in a boxing punch. Yeah? And we measured the stresses in the horizontal plane, right? And you'll expect that they are high because there's all this rotation taking place. But then we also from the analysis, got the stresses. The stresses is a measure of the force, if you want, happening inside the body in the vertical direction. And we found out that they were comparable, which is scary, but it's in fact, intuitively, you can understand it now from the pointing effect I was telling you earlier. Since the brain is rotating and experiencing some torsion in this plane, it's going to push up on the skull in the vertical direction. So it's really bad news to get rotational impact to the head. Whew. The interlude within the interlude. Now, I hope there's no student of mine because they know all the answers, but if you do, don't. If you've seen it before, don't say it. But it's literally a maths movie quiz. I'm going to give you a quiz where you have to guess the title of a movie from a mathematical clue. How about that? Are we ready? So, which one is this? Next on the plane. Which one is this? American Pie. What's this the symbol in maths?
Universal.
Yes, so it's reunion. Whoa. Which one is this? So you know this is pi. Which number is that? Oh, sorry, it's a fact of science. Yes, Fiona?
Wally.
Very good. That's the number E. Okay. Calm down, calm down. We're going to get through this together. What is this? What's this the symbol of? The sum from I to n of this object. And then I divide the sum by the number of the objects. What am I doing? I'm computing the average. What's another word for average? Mean. The top one, that's physics now. All right? When t is smaller than t0, f is 0. When t is greater than t0, f is not 0 anymore. Which one could that be? What happens at t0?
Inception.
Sorry? Inception? Okay. My guess, T0 is time inception. No, that's, what is F in physics? So, what happens at T0? Yes! The Force Awakens. Finally, I came up with all this stuff. What do we have here? R's. Somebody's going to find it. Yes. What about those R's? The letters. What's the other characteristic?
Radius.
The red R's.
Of the arc.
Of the lost ark. Very good. Okay. So, I'll show you about destructive testing. Now you get why it's called destructive, because I gotta cut those pieces of brain. Nobody wants to volunteer for that, right? Another way is to do non-destructive testing, what's called brain waves, literally brain waves. And this is what we did. So here we have the brain of a pig. The pig is dead. No PhD students was are in the experiment. But you can see that the brain is intact now. right? I don't need to cut it into pieces, don't need to destroy it. In principle, I could do it on a live animal. I'll just need to do a cranioctopy, which is hard on pigs because their skull is about 5 centimeters thick. But what you can see is a beautiful brain. Actually, it has a sulci and it has circumvolutions. It's pretty advanced. A pig is actually really intelligent in many ways. In any case, we use this probe here that gives you ultrasonic image of what's underneath, in this case the brain. And then on top of that, superposes a wave. So there's a wave traveling through the brain, and the machine tells you the speed. Here it says it's about 3 meters per second, which is really, really slow. If you think of waves in seismic waves, for instance, it's about 3 kilometers per second. So it's really slow because the brain is really soft. And so just like the string of a guitar will vibrate at a high frequency, would vibrate really fast if it was really taut, and much slower if it was a bit slack. It's the same for materials. If they're stiff, the wave travels fast. If they're soft, it travels slowly. And then from these measures, we're able, again, to get access to those quantities I was telling you about that are so important in simulations. So here, I just want to show you this research is not just me, it's all over the world, in a few centers in the world. And it's really an exciting research topic. For instance, this person here in UCL, so that's University College London, and in collaboration with doctors, surgeons in the Great Ormond Street Hospital in London, they did experiments on patients with tumors, brain tumors. And brain tumors, if you were here last year, my PhD students were telling you about this. Brain tumors usually are detected by what's called palpation, which just means poking at your brain with the finger. I said, this is soft. Oh, this is hard. Should be here. So that's not very precise, right? It's not very satisfying if you're a scientist. If you do it with just ultrasound, you can see here that there's a region where something is happening, right? It's probably denser here. Sorry, it's not an X-ray. It's stiffer here. The sound seems traveling faster over here. But if you do it with that way I was telling you about, the one we superimpose on top of the ultrasonic image, you get very good contour now of the brain. So this is on humans, live humans. There was a trial with about 12 patients. The conclusion was that shear-wave elastography was in fact superior to the surgeon's opinion in locating the tumor. Amazing. And now I'll show you an even more amazing result is that you could say that the limitation of this technique is that you need to access the brain, right? Because those elastic waves, they don't go through the bones, but you could do it on infants, because infants have a fontanelle, right? For the first 6 months, the two hemispheres of their skull have not met, and so there's a region where there's no skull, and so you could do the imaging directly underneath. And this is what they've done here in France. An amazing setup. It's very easy. That's the machine. It just takes very little room. Much easier to do that on a live baby, than to do MRI. Because for MRI, you have to stay, it's not still for 10, 20 minutes. Go try to tell that to a newborn baby. Okay, that's my end slide. Thanks for your attention. And I need to mention my sponsors, the Irish Research Council and the French Embassy. Au Liban, that's not true. It's the French Embassy in Dublin. Sorry about that. I put all this together 5 minutes ago. Okay, thank you very much.